welcome to the lecture of subject digital signal processing KEC 503 on the topic finite impulse response filters and their designing. If for any linear shift invariant systems, the output is denoted by y of n and the past outputs are denoted by y of n minus k for summation of k and change of amplitude, and present and past inputs are denoted by x of n minus k. As the summation starts from k is equal to 0, x of n also is there, therefore present is also there, and past s of n minus k. So, if yn depends on past outputs and present and past inputs, then the system is said to be an IIR system. If the values of AK become 0, that means there is no dependency on the past outputs of the system. Then the system is said to be what are called finite impulse response systems. Finite impulse response systems, FIR systems, where the equation for the present output will be in this summation starting from k to m bk x of n minus k. If we model this system as a filter h of n and LSI filter, and the input is x of n, the output is y of n, then y of n is basically x n convolution h n, and h n is the impulse response of the FIR system, which is a commutative convolution is a commutative operation. So, either we use h of n minus k in the summation or x of n minus k in the summation, and since it is truncated and causal, the summation can be represented like this, that y of n is equal to summation k from 0 to m h k multiplied by x of n minus k. After the summation is over, we will get y of n. Now, if I just compare these two equations, you can see that the bk's are nothing but the hk's. The bk is nothing else but the h of k's. Now, the bk's are called the coefficients of the FIR systems, and in this case specifically FIR filters. So, these are the coefficients. The coefficients are actually equal to the impulse response of the system since it is truncated. So, in this manner, if I want to evaluate the transfer function or frequency response of the system, the transfer function will comprise of elements bk only. So, in simpler terms, if we want to define the impulse response of FIR systems, we only need to evaluate the coefficients and vice versa. If I want the coefficients, I only need to evaluate the impulse response of the system. The impulse response of the system is basically the inverse Fourier transform of its discrete time Fourier transform. So, if there is any given specification of HDN in terms of impulse response, then HD of Ej omega is Fourier transform of the impulse response HD of n, which is a DTFT operation, discrete time Fourier transforms. This is a discrete time Fourier transform operation. So, from the frequency domain representation, we can obtain the time domain representation by evaluating inverse DTFT. inverse DTFT. Inverse DTFT for any frequency response HD of Ej omega is the frequency response multiplied by e raised to the power j omega n and integrating with respect to omega 1 upon 2 pi, and what we will get is HD of n. The limits of the integration depends on the properties of HD of Ej omega. So, the frequency response is periodic and the periodicity is 2 pi. So, in an interval of 2 pi, if we evaluate the integral, we will get the same result. So, it is periodic from 0 to 2 pi, from 2 pi to 4 pi, and so on and so forth. But it is generally mathematically more convenient if we evaluate this integration within the limits which are symmetrical or anti-symmetric for that matter. So, we evaluate the integral from minus pi to plus pi, it is the total difference between the limits is 2 pi. So, it is periodic with 2 pi, whatever happens between minus pi to pi is what will happen between pi and 3 pi also. So, in this manner we can evaluate HD of. Now, when we are given the proposition of designing the FIR filters, a specification is given in terms of frequency response. What is the pass band ripple, what is the stop band ripple, what is the magnitude spectrum that is required. Now, if that spectrum is given to us, we need to evaluate the impulse response of the system. Why? Because the filter coefficients are actually equal to the impulse response for an FIR system. This we have seen. So, for an FIR system, the impulse response is directly equal to the coefficients of the filter. So, if I want to design the filter, I want to obtain the values of B of n, and in order to evaluate the B of n, we require to find H of n, and H of n will be obtained from the given desired frequency response. Now, what is to be understood at this moment is that when we evaluate the inverse DTFT, this HD of n in time domain is from minus infinity to plus infinity. This is not truncated. So, what we will get is HD of n, an impulse response which is existing from minus infinity to plus infinity, which means from the previous equation, which means that it does not belong to the second equation, it rather belongs to the first equation. It has infinite terms, and therefore, this HD of n is actually an infinite impulse response filter. Impulse response, it is a response which is infinite. What we want to do, we want to make it finite. We want to make it finite. So, the problem for FIR designing is how to convert HD of n into conversion H of n, so that minimum we approach very near to the required specifications, because HD of n is consisting of infinite terms. If we will truncate, we will omit out few terms, we will lose out on information. So, obviously, we will not be able to meet the exact specifications, but we will come as approximate as possible. So, the basic problem is to convert the infinite response into a finite response, then it will become a finite impulse response filter. So, this generally the problem that is given to us for a case of low pass, I am just discussing here. A high pass also can be done similarly. So, if it is a low pass system, we generally are given a frequency response like this, that between minus omega c to plus omega c, some cutoff frequency, the frequency response is e raised to the power minus j omega tau, and it is 0 otherwise. Generally, this is what we get, it is 0 otherwise. If we look at e raised to the power minus j omega tau, which is the HD of e j omega, you can understand this is cos of omega tau and minus j times of sine of omega tau, isn't it? This is by Euler's theorem, this is what we get. And if we talk about the magnitude in this case for HD of e j omega, the magnitude is 1, because it will be root under real square plus imaginary square. The imaginary part is minus sign, the real part is cos sign. Root under cos square plus sin square is 1. As far as the phase part is concerned, the phase part is concerned, it is tan inverse. It is basically tan inverse. I shall write this because it is important. Minus sine of omega tau upon cos of omega tau, which becomes minus, this is sine upon cos will become tan. Tan inverse of tan is the theta. So theta is tan inverse being an odd function, the negative sign will come. So we can understand the phase is represented by minus omega tau. So the magnitude is unity. The magnitude is unity and the phase is linear. This is very important. So generally the problem that we get in FIR filter designing is of this shape. It is from e raised to the power minus j omega tau, tau being a constant, between minus omega c to plus omega c, and it is 0 otherwise, and this corresponds to a linear phase system. So we basically generally have a problem of solving, an important problem is linear phase systems. How do we design the filter? We firstly obtain the IIR response, the HD of n. How do we evaluate the HD of n? By calculating the discrete time Fourier transform. And how do we calculate the discrete time Fourier transform? 1 upon 2 pi integral minus pi to plus pi HD of ej omega and e raised to the power j omega and d omega. So let us see this just for an example. Suppose we have a specification of a filter, but the value of tau is 3 basically, and it is from minus omega c to plus omega c, which is minus 3 pi by 4 to plus 3 pi by 4. Firstly, what we evaluate is the dt inverse dt of t, for which we just use minus pi to plus pi hd of e j omega e raised to the power j omega and d omega. Now if we understand the proposition, this otherwise means that it is 0 between 3 pi by 4 and pi. So which means if we put this function, so we will put this function, we'll substitute the limits also. So how do we substitute the limit? The limits become minus omega c to plus omega c, and this remains to e raised to the power. This actually can be combined and written e raised to the power j omega and n minus 3, and you can remember the values of omega are from minus omega c to plus omega c. If I evaluate this, the impulse response that we are getting is sine 3 pi by 4 n minus 3 divided by pi n minus 3. Of course, the denominator becomes 0 at n is equal to 3, therefore it is defined only for n is not equal to 3. hd of n, however, one can, I think it will be 3 by 4 from L hospital rule, just differentiate the denominator and numerator once and put n is equal to 3. You differentiate the numerator and denominator once, you put n is equal to 3, because at n is equal to 3 it is not defined. Then you will calculate a limit, L hospital rule. You will get the value of impulse response at 3 by 4, 0.75 for n is equal to 3. So in this fashion we can evaluate the inverse discrete time Fourier transform of the system. The inverse discrete Fourier transform, if we evaluate, will be of infinite length. Since we are dealing with finite impulse response system, what we want to truncate this, and to obtain the FIR HN, we actually use HD of n multiplication by some function which is called a window function. Various functions have been proposed in the literature. So window function will be from 0 to m minus 1, which means the length will be m, and if I multiply this, now this is actually existing from minus infinity to plus infinity in time. It multiplies by something which starts at 0 and ends at minus m minus 1. So before 0, hd of n will not come as in hn, and m and onwards hd of n will have h of n will have no component of hd of n, which means we will actually truncate this by multiplying by a truncated impulse response, which is called a windowing function. So we generally use window functions just for an example and for the current situation. I have illustrated using Hamming window. So what happens is that we calculate the value of HD of n for values of n and W of n. W of n is by putting n and m. In this case, we will have actually m minus 1 will be 6. Basically, it is the function that was given to us. In general, if it is e raised to the power minus j omega tau, then tau is m minus 1 by 2. This is the general structure. So, of course, in this case tau was 3. So, we will have m is equal to 7 and this means that m minus 1 is equal to 6. So, we will vary from 0 to 6, we will evaluate HD of n, we will evaluate Wn, Wn remains fixed, and we thus obtained the designed FIR impulse response, which are also equal to the Bn of the system, interestingly. Now, what is important to note here is that since we started with linear phase frequency response, you can see from the rightmost corner, right, it is also apparent from each side. So, HD of 0 is basically equal to HD of 6, HD of 1 is basically equal to HD of 5. Similarly, HD of 2 shall be equal to HD of 4, and the middle term is H of 3, at which the impulse response was not defined, we evaluated using L'Hospital rule. So, you can see that this is equal to this. Same observation can be made for the window function as well. You can see from both the terminals they are equal, isn't it? From both the terminals they are equal. It is unity at n is equal to 3, the midterm. And due to the symmetrical structure of if the multiplication takes place, of course, it will be symmetrical. It will be symmetrical, isn't it? The terms are symmetric. So, what we are observing here, which is a very standard rule, is that H of n, the desired filter, is actually equal to H of m minus 1 minus n, and this is only applicable while designing FIR impulse response for a filter which is having a frequency response which is linear phase. Linear phase means there is the magnitude response is unity, the phase response is constant. So, if that is the case, then we can just actually evaluate the half of the calculations and remaining half you can directly write, because it is given that the frequency response of the system is linear phase system response. Now, what is the reason this takes place? So, first of all, what is the importance of linear phase? The phase part plays a very important role in communication systems. Phase noise is the most important while transmitting the signal, because it brings random shifts to the signal. Therefore, what we want is that the phase is constant, but in FIR systems we are truncating, we are not using the complete HD of n, rather we are multiplying HD of n with W of n and keeping some parts from 0 to m minus 1. Therefore, it is not possible to meet all the specifications, and therefore, it is not possible to meet constant phase specification. Then we make a compromise and say that okay, if we cannot meet the constant phase, if we can maintain at least a linear phase, then that will be of immense importance. So, if that happens, we actually have this condition that we saw in the last slide. H of n is equal to H of m minus 1 minus n. So, this is the condition for maintaining linear phase FIR filters. What is the meaning of linear phase? Suppose I have any frequency response DTFT of a system which has some magnitude portion and some phase portion. You can see in this case the phase portion which is written is j alpha omega plus j beta. So, if I talk about the phase, it is actually minus alpha omega plus beta. Now, there is an entity which is called group delay, and group delay is basically the minus derivative of the argument h e j omega. So, in this case, if I do that, if I put the phase of the system here, then you can see that this derivative is basically a constant alpha, which means that the group delay is constant. The group delay is constant. If the group delay is constant, appears that the phase is linear. So, phase is linear in frequency domain also becomes that the group delay is constant. So, how does that condition arrive? Suppose that we have a magnitude response capital H of e j omega, which is some magnitude and phase. By Euler's theorem, I can always take the j part common, and e raised to the power j theta can be written as cos theta plus j sin theta. If I use this, you can see this is basically what beta minus alpha omega, which comes here, isn't it? So, I have a of e j omega and plus j e of e j omega and cos and sin. So, this is the representation of the magnitude response. Now, how does we get the magnitude response? The magnitude response is actually discrete time Fourier transform of the impulse response. How do we evaluate discrete time Fourier transform? Summation of n from minus infinity to plus infinity h n e raised to the power minus j omega n. I can again use the Euler's property, e raised to the power minus j omega n is equal to cos omega n minus j sin omega n, and h of e j omega can be written as in place of e raised to the power minus j omega n, I can write cos omega n minus j sin omega n. So, I can multiply this, since summation is a linear operation, I can take the both summations out. So, I basically have the frequency response becomes equal to h n cos omega n minus j sin summation h n sin omega n. Remember, this is the same h e omega that is that we have evaluated previously. Now, if we talk about the previous equation that we derived, the previous representation was h e j omega a e j omega cos beta minus alpha omega and sine of beta. So, if I evaluate the argument appears to be sine upon cos, and these portions will cancel out. So, if that happens, is actually equal to sine of beta minus alpha omega, the phase part, when we evaluate using the frequency response which is given. When we use the definition of the DTFT, then this again happens to be a ratio of sine by cos. So, remember that these two things are actually equal because the frequency responses are equal. So, what we can do? We can equate the two. I will equate the two. So, if I equate the two phases that we have evaluated, remember we are calculating for linear phase. So, the phase is what we are evaluating by two different equations, and we are trying to equate the two to obtain the results. Now, if I look at the two, the first one is sine beta minus alpha omega upon cos beta minus alpha omega. Here it is minus summation for n all values h n sin omega n and summation for n h n cos omega n. What I can do? I can cross multiply. So, if I cross multiply, I will have, so this portion comes here. So, h n cos omega n multiplied by sine alpha omega, and the negative sign summation n minus infinity to plus infinity h n sin omega n cos beta minus alpha omega. Now, it is very easy to bring the right hand side on the left hand side. That we can do. We can bring the right hand side on the left hand side, the negative sign becomes positive, and now we have two summations in which h n is common. the summation limits are in fact common, so we can combine them. So two summations can be combined, and this should be equal to 0. This should be equal to 0. If I look at now, it becomes Hn sine beta minus alpha omega into cos omega, and cos beta minus alpha omega into sine omega n. A very simple trigonometric identity can be used, sin A cos B plus cos B sin A. So what we can do, we can just use this property and we can combine the two angles. The two angles will be in constructive manner will be combined. So first angle is beta minus alpha omega, second is plus omega n, which becomes to 0. I can take the omega portion common and rewrite it, that the condition that we are establishing is that summation of n for all values of n, h of n multiplied by sine omega n minus alpha plus beta is equal to 0. If this is satisfied, then the filter is linear phase. So we want a solution to this. Now the necessary condition for the group delay to be constant or the phase to be linear is that this summation is 0. The solution to this is not easy to get, but the solution of one of the solutions is when the value of beta is basically 0 and pi. So if it is 0 or it is pi, in both the cases we get two things. So this is the case for symmetric. This is the case for symmetric, and this is the case for anti-symmetric actually. Anti-symmetric. So in both the cases actually this is what we will get. So the solution that satisfies this equation is that beta is equal to 0 and pi. The constant alpha is 2 alpha is equal to m minus 1, and it has to be an integer, and therefore the impulse response h of 2 alpha minus n shall become equal to hn. So the symmetricity that we are getting, and if this is so, you can understand that alpha is basically m minus 1 by 2, which was in our numericals also. It used to be tau then. So if in place of alpha I write that, it becomes h of m minus 1 minus n is equal to hn. So very importantly, this is the condition for maintaining linear phase. Okay. So the proof of linear phase comes from this, that we calculate the phase of the system, the same frequency response using either DTFT and by Euler's theorem. We equate them, we solve the solution, solve the equation to get a solution. The solution provides the criteria on the impulse response, that they are equidistant from both the ends, that we have seen in one numerical also. So either using a windowing function or using any other means, if the linear phase is there, the FIR filters, the impulse responses which are actually equal to the filter coefficients are equidistant from both the ends, and that completes the proof and the lecture. Thank you.